In this video, we'll be talking about the ratio test. Suppose that you have a series like this, and let L to be the limit as n goes to infinity of the ratio. This is why this is called the ratio test. So what is the ratio of? You're going to do the n plus 1 term divided by an. If we use absolute value, if you get the series to converge, then it's called absolutely convergent. Once you figure out this limit, which is the whole part of the test, you're gonna get three different answers, or you're gonna look for three different answers. If the limit is less than 1, then the series is convergent. If the limit is more than 1, the series will be divergent. And if the limit is equals to 1, the test is inconclusive, which means the series can either be convergent or divergent, and you're going to need to use a different test, like the integral test, the comparison test, or any other test. Before we do an example, when we do the limit, it's very important that you understand what, to get the an plus 1 term, all you have to do is substitute whatever you see n for n plus 1, and we'll demonstrate that in the example. In this example, the absolute value will get rid of this part, so you don't have to worry about this. An is n squared over 5 to the n. So therefore an plus 1 will be n plus 1 squared over 4 to the a plus 1, which this simplifies to n squared plus 2n plus 1, and on the bottom this is 5 to the n times 5. We find the ratio. So the ratio a plus 1 over an will be equals to n squared 2n plus 1 over 5n times 5 times 5 to the n over n squared. All of this is on absolute value. Here we can cancel this, and we don't need the absolute value anymore. This is n squared plus 2n plus 1 over n squared. Now we apply the limit. So the limit as n goes to infinity of the ratio is the same thing as the limit as n goes to infinity of n squared plus 2n plus 1 over 5 n squared. The limit is equals to 1 over 5, since the two equations, or the two expressions, the biggest exponent is n squared, you just divide, or you can use L'Hopital's rule and you end up with the exact same answer. So the limit is 1/5. All we care here is to check if this is more or less than 1. So 1/5 clearly is less than 1, so that implies that the series converges by the ratio test. Actually, the series is absolutely convergent because we use the absolute value. Let's move to the following example. Here an is n to the n power over 4n times n factorial. Therefore an plus 1 is n plus 1 to the n plus 1 power divided by 4 to the n times 4 times n plus 1 factorial. If we simplify a little bit more here, n plus 1 factorial is the same thing as n plus 1 times n factorial by the definition of factorial. And this you can write it as n plus 1 to the n times n plus 1. Hence, this simplifies a bit more, and this is what we end up with. It's a very good idea to simplify as much as you can before you put it in the ratio test. So this is what we have left. Alright? Okay, so now if we apply the ratio test, the limit n goes to infinity of the absolute value of the ratio is the same thing as the limit as n goes to infinity of the ratio of n plus 1 to the n over 4 to the n times 4 times n factorial times 4 to the n. All I'm doing here is just multiply by the reciprocal since you are dividing into fractions. Okay, so what can we cancel here? You can cancel the n factorials, the 4 to the n, and we're left with the limit as n goes to infinity of 1/4 times n plus 1 to the n power over n to the n, which is the same thing as the limit as n goes to infinity of 1/4 times n plus 1 to the n over n to the n power, which is the same thing as the limit as n goes to infinity of 1/4 times 1 plus 1 over n to the n power. Recall from previous sections that the limit as n goes to infinity of 1 plus 1 over n to the n is equals to e, which is around 2.71. So therefore, we end up with 1/4 times e, which is less than 1. So therefore, this series is also convergent by the ratio test. Right?